Hello everyone. Today we are going to present the paper on vector quantized diffusion model for text-to-image synthesis. This paper was published in CVPR 2022 and it has 119 citations. This will be presented by me, Manu, Prudvi, and Adil. So let's go through the agenda. We'll be discussing the existing methods. We'll be discussing the diffusion model itself. We'll discuss the forward process, reverse process. We'll also go through the experimentation details, ablations, and conclusion along with the demo. Let's start with the existing methods. The first existing method was the GAN-based methods. These models generate high fidelity images on single domain datasets. But since they have inductive bias, they struggle on complex scenes, and they also cannot, they require fine-grained object labels. They are only limited to single domain images. Coming to the next model, which is auto-regressive models. These have shown powerful capability of density and estimation have been applied to image generation recently. Pixel RNN, image transformer, image GPT are some of the examples. But these also generate low resolution images and also struggle with a unidirectional bias, accumulated prediction errors, and they're also slow in inference. Now let's go to denoising diffusion probabilistic models. Most previous works on diffusion considered continuous diffusion models on the raw image pixels. D3PMs apply discrete diffusion to image generations. Here we are having the forward diffusion process and reverse denoising process, as we all know. And these also have limitations, such as it can only generate low resolution images, and also they also only estimate the density of raw image pixels. Coming to the latent diffusion model, which we have discussed earlier, what we see is that they decompose the image formation process into a sequential application of denoising steps, denoising autoencoders. So what that means is that they take the image in the pixel space and encode it using an encoder and follow the diffusion process in a latent space. And then the image is reconstructed back using a decoder here back to the pixel space. Similar to this idea, we come to the VQ diffusion model, where the model is presented for text-to-image generation using two steps, which are VQ-VAE and the VQ diffusion. VQ-VAE is used for reducing the context length, and the VQ diffusion models the discrete latent space. Let's discuss the variational autoencoder further. We know that an autoencoder is a neural network which is designed to encode an input image into a meaningful representation and then decode it back to reconstruct the input image as to the original image as possible. But what variational autoencoder does, it provides a probabilistic manner for describing an observation in latent space instead of encoding it as a single point. They encode it as a distribution over the latent space. So we get from the output a mean and a variance from the image. And then the decoder is able to reconstruct it back to the original image. So let's see what VQ variational and autoencoder does. VQ-VAE encodes image from pixel level to discrete token level. So this model consists of an encoder, a decoder, and a codebook containing a finite number of embedding vectors. So what happens here is, given an image X, we obtain a collection of image tokens with the encoder, and then using the quantizer function, we are able to map these tokens to a 2D representation using a codebook which is of length k. Let's further discuss this in the next slide. So we have this, we define this latent embedding space where k is the size of this vector and d is the dimensionality of each latent embedding vector. So what happens in the encoder is nothing but using a CNN, we are able to generate vector zx. And then as the model takes this input x, it is passed through this encoder, and then the discrete variables z are calculated by a nearest neighbor lookup using the embedding space given here. And we are able to create this ZQX using this quantizer function. The input to the decoder is the corresponding embedding vector, which is passed again through an CNN to reconstruct back the image as shown. Now the second step, which is VQ diffusion, this is nothing but it models the discrete latent space by reversing the forward diffusion process. The forward process yields a sequence of increasingly noisy latent variables of the same dimensionality as the input given, producing a pure noise after a fixed number of steps. Starting from this noisy result, the reverse process gradually denoises the latent variables towards the desired data distribution using this diffusion image decoder at every step. What this diffusion image decoder contains, it contains the blocks as shown here, and it also takes in two additional signals, which are nothing but the time step t here, which is indicative of the step in the Markov chain. And another is the text token, which is given by the text encoder here. And then these two signals are given to through the adaptive layer normalization block and the cross attention respectively. The T is given to this, and the text output from here is given to the transformer block as shown here. And further VQ diffusion will be explained by Manu.
Thank you, Mukund. So now we will be looking into more detail as to what vector quantized diffusion has to offer. So going back, we have the normal diffusion, denoising diffusion process. We have an image like this, and essentially we take that as the initial step in the diffusion process. Then we add Gaussian noise gradually and get extend and until we get a sample from a standard normal distribution. So this we essentially call as the forward process, and denoising or getting the image back is what we call the backward process. This is this typical denoising diffusion process. So what vector quantized diffusion has to offer is, it's very simple, it's very straightforward, and it's very exactly similar steps are performed like in any standard diffusions, but the diffusion processes are not performed on the input image space or the pixel space, but rather, as Mukund has pointed out, we have a 2D code representation from the encoder of a VQ-VAE. This diffusion process is basically done on this 2D code representation space. More specifically, we will have this code representation as the input. We will gradually add noise in the forward process to obtain significant subsequent steps. And here you can see that I have marked these entries as star because we will discuss further as to what the star has to offer. So this is the forward process. And in the reverse process, again, we try to denoise the noising process and obtain the input code representation. So now the biggest question is, what will be the noise process? How will we add noise? So in a typical standard diffusion, we will say that we will add, since it's pixel space, continuous space, we will add Gaussian noise. But here, if you have noticed, these individual entries are not continuous, but rather the position or the token that we have selected to replace in the VQ-VAE. So what will be the noise process? The authors have essentially given replacement of tokens. They have suggested we will do replacement of tokens. What essentially that means is, we will have a 2D code representation. What we will do in subsequent forward steps is that we will replace randomly individual tokens. So in this case, I have marked it with red. This kth token, this represented that at this position, we are taking the kth token from the code book that is replaced by a random 5th token or random entry 5. For this 3, we have replaced this with 2, subsequently 5, 1, 3, 7, 9, and 4. That is the first forward step. In the next subsequent steps, we keep on going that, and this is essentially our forward process. And in the reverse process, we try to denoise this process. We try to eliminate this noisy process and get the input code representation that we try to give. Again,
Generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Now, again, the second biggest question, how can we perform this? How will we figure out? How will we do a denoising process on this newly introduced noising process? So before going into details, let's just go back again to our standard diffusion. We all know that a transition probability we have xt given xt minus 1 is a normal distribution. And the mean and variance are a function of the beta t that the user provides, right? So since this is a Markov chain, Markov process, we define it as Markov process, we have the Markov property that all the intermediate time steps or all the time steps in the Markov chain, the joint distribution conditioned on the first initial input is nothing but the multiplication of all individual transition probabilities. If you do a little bit of mathematics or algebra, you will figure out that we can actually marginalize all the intermediate steps and directly jump to any arbitrary tth step given the input image. This is basically saying that we have one image, then the first, then the second, then the third. So we don't have to do directly all that. We can just directly skip to any arbitrary time step t. And luckily, the algebra worked out, and we figured that that's also is a normal distribution where we have a new mean and a new variance, and this alpha bar parameter is given by this given equations. This is all known facts. So instead of calling this standard diffusion, we can call it continuous diffusion. Why? Because the variables involved in the latent space is continuous in nature. But in this case, where we are right now talking about is the variables involved are discrete in nature. So the transition probability distribution we were working on, the continuous transition probability distribution won't work, and we need something called a discrete transition probability distribution. So the authors again proposed that why don't we use the categorical distribution? So this is our representation for the categorical distribution, where pi is essentially the probability of this ith category occurring. Moving forward, since it's a Markov process, we can directly use the transition matrix techniques in here and figure out what is the transition probability. Here, Qt is the transition matrix like any Markov chain processes has. And V is actually a one-hot column vector whose length is k. Again, remember, k is the number of code vectors we have in codebook. And only that entry is one where the input x is. So as an example, if I say Vx equal to 3, it essentially will give me one hot column vector of length k. This length is k. And the third entry will be 1. So moving forward, what this essentially means, let's just get this into more context. In a normal diffusion, we say that we have, let's just say at time step 9 and time step 10, we have some 2 samples. So what essentially we have is in this step, we have a transition probability Qx10 given x9. Again, as a reminder, this is the standard diffusion process. And what essentially it means that the x10 or the 10th step image that we had is actually a sample of this distribution, just to get things into context. In this case, in the standard diffusion, you know that this is a normal distribution. But in our case, the input, the image space or the latent space is not pixel space, but rather the discrete code representation space. And the probability, the transition probability, is a categorical distribution, which we again, as we saw, is represented by this equation. We transpose xt, qtv, xt minus 1, where qt is transition matrix and vx is the one-hot column vector. Now, there is a little bit of caveat. All these discussions that we did is not for the entire image space, but rather for individual entries. So whatever we discussed so far, the categorical distributions, the transition probabilities, all these are for just individual entries. So for all these individual entries, we will have the corresponding transition distribution or transition probability distribution as well. So just to make things simplified, we will omit this superscript and keep on discussing with this current setup. So now this is the equation, the transition probability. Let's just now look into what Qt has to offer, the transition matrix. So for any arbitrary k equal to 3, let's just say that in my code book, there is 3 code vectors. Qt will look something like this, where individual entries will give me the transition probability for individual states. So here state means code vector. So if I say k equal to 3, I'm saying there are 3 states. So what is the probability that if the xt minus 1 state is 1, and in the forward process, on the next step xt, what is the probability that this state will remain at 1? And this entry essentially says that if it's 2, what is the probability that the next state will be 1? And the last entry essentially says if it's 3, what is the probability that's still going to be at 3? This is essentially standard transition matrices. And if you look at any arbitrary k values for any arbitrary k code vectors, we will have something like this. Again, the statement holds that first entry essentially gives if the previous entry is 1, what is the probability that's going to stay like that? And the last row in the first column gives us what is the probability that this current state from 1 will jump to k in the next time step. Putting it all together, we will see something like this, which is the transition probability. We have all the equations hold. VT we have already seen. Now the biggest question here now is, what is the values of these things? Because if you remember in the standard diffusion, we were talking about betas, alphas. There we had the control over the Gaussian distribution or the normal distribution that we are considering for the transition probability distributions. So we had the betas, we had the alphas. We used to control all these values. Here, so far, we haven't seen anything like that. So that's where the authors point out the transition matrix is the control that we need in this entire Markov chain process, where they define the transition matrix in the beginning as alpha t plus beta t, and all these entries. Here you can see that the diagonal elements are all the same, alpha t plus beta t, and all the beta t's, all the other elements, non-diagonal elements are beta t's. If we match it, this equation again stands like previously. And if we match it with the standard definitions of the transition matrix, we will know that the probability for any time step t minus 1 being 1, and the next time step, it will remain in 1, is provided by alpha t plus beta t. This is the probability that this will happen. What is the probability that the current state is k, and in the next state, we will go to 1, it's beta t. So all the diagonal elements is alpha t plus beta t. This essentially means that what is the probability that I am at any current state A, in the next state, I will remain in that particular state. It is given by alpha t plus beta t. What is the probability that I will jump into any other states? K minus 1 beta t. Moving forward, we again have this equation. It's going to come up a lot. And since it is a Markov process, we can do pretty much what? Integrate or eliminate all the intermediate time steps. Basically, we call it marginalizations in intermediate time steps. We can perform that, and we can directly jump into any arbitrary time step like we did in the normal distribution case or the standard diffusion case. And luckily, we again find out that it has the same analytical form, except the Qt is now Qt bar, where Qt bar is nothing but the individual multiplication of all the transition matrix till time step t, starting from time step 1. So now let's just put it all together. What this essentially means visually is that we have for any arbitrary time step t minus 1, we have some code representation. We will have a transition matrix as well. Since again, we were talking about arbitrary individual entries. So for every individual entry, we will have a QTI. So let's just look at this particular entry here, which is 4. What it essentially means that this 4 in the next step, which is xth step, this 4 can jump into any of these categories. 1, 2, 3, it can remain in 4, or it can go to 5, and so on until the kth vector. So it can change to any of these k values. The transitions, the chance by which these 4 will get transferred to any of these categories is given by the transition probabilities from this transition matrix that we defined. So the probability that in xt, this 4 will change to 1 is xt equal to 1, given xt minus 4, and so on and so forth. It's pretty straightforward. Moving forward, in vector quantized diffusion, what we essentially have is, let's just say this is the input code representation. In the forward process, we will use the Q1 transition matrix and replace the tokens. I have here marked with red all the tokens that have been replaced. Then we'll use the Q2 to get X2, and then Q3 to get X3, and so on and so forth. In the back. And then there is another thing that here you can see that since we have defined how to marginalize all the intermediate distributions, we can directly use xt given x0 to directly jump from x0 to x3 using this analytical form. And if you want to further simplify it, it is nothing but q of x3 given x0. We can do it with vt x3 q3 bar vx0. There are some issues with this particular step although we might seem that, okay, everything works out, but there are some issues with this approach of replacement of tokens. The first issue is that, let's just say, for simplicity, let's just say that this third token focuses or represents the head or partial head of a cat. So it's pretty semantically sensitive that the seventh will also be looking at something similar to a cat's body. So this is just a simplified representation. Since we are randomly replacing and uniformly replacing these tokens to arbitrary tokens, it can occur in any time step that we replace this 7 with a kth token. But the kth token essentially focuses on a tree-like structure. So this arbitrarily and suddenly changed the entire semantic nature of the code representation. Why? Because we just randomly changed a token to any arbitrary step. That's one issue. The second issue is that, let's just say that we have xt and xt plus 1. This is 2 steps, adjacent steps in the diffusion process. In this process, we have no idea as to see which all tokens were replaced. Just because here I have shown you the tokens that are replaced with red, but the model has no way to know at this current stage which all tokens were replaced. So what is the issue with that? First, it increases the model's toughness in the denoising process. Essentially, what it means that the model first has to figure out which all tokens were replaced before putting the correct token at that place. So it's like increasing the complexity of the task. Also, let's just say that the model thinks the 1 is the one over here is the one that is replaced. So since I previously mentioned that all these tokens are not independent, they have neighborhood conditioning. So they are semantically conditioned. So if there is a 1 over here, there is a very good chance that, let's just say that 7 cannot come around here because 7 represents maybe a fox's tail and 1 represents a wall. So it cannot come together in most of the cases. There is very less probability. So model will say, okay, 1 is the noisy one. So let's just replace 1 because 7 and 1 cannot be neighbors. But in fact, 7 was the replaced one and 1 was at its correct place. So what it essentially induces is a competition. They say the model itself fights among these tokens saying, okay, 7 is the correct one. So with 7, which should be the semantically accurate thing to place over at the place of 1. And if 1 is the correct one, what is the semantically accurate place to place at 7? So it induces a competition. What is the
generated images, self-driving cars, augmented reality, virtual reality, it's all around us.
Solution to this? This is what the authors propose: mask and replace diffusion strategy. It's very simple and straightforward. What we already had is k code vectors. The authors propose we will add in a new mask token or a new mask state, or you can say vector. It's not a vector, it's just a state, just a category. What they do is, instead of having just k categories, we will be having k plus 1 categories. So what is this mask category? So before moving into what mask category is, let's just look at, since the state space has changed, we will look into the transition matrices as well. So the transition matrix in the top left corner is exactly the same. You can see that it's exactly before. It's just that we have added a new row and a new column. So in the new row, you can see that a new parameter has been introduced, which is gamma t. And here we know how to obtain gamma t from alpha and beta. So how we can set gamma t and obtain alphas. And what it essentially means is that if we compare it with the definitions we had, this new entry that we have essentially is giving me the transition probability that the previous state is 1. What is the probability that this state 1 will jump into the new introduced state mask? So this probability is given by gamma t. So that row is clear. What about the columns? The columns gives us that the current state is masked. What is the probability that we will go to any other state 1 to k? But here you can see that all of these probabilities are 0, which essentially means that if any of these tokens jump to the mask state, it's a dead state. We will never move out of it. The probability of moving out of it is none, and the probability of staying there is universal, which is 1. What it visually means is that here you can say that in arbitrary steps I have shown you, these mask tokens. So in the very first step itself, the first token jumped into the mask token. Now, no matter the time steps, even if we go to infinity, this mask state or mask step will always be in mask state itself. What is the advantage of it? The advantage is that now the model has a way to know which all tokens or which tokens were for sure modified. For sure modified. So now the competition has been reduced, because if the model sees an M, it definitely knows, okay, this has been replaced. So let's just fix this one. And then we will condition all the neighbor tokens on this particular fixed token. That's the advantage. So mask and Variational diffusion strategy right there in the forward process. Now, only one final piece is left. In the last distribution, or the last distribution that we use in any standard diffusion process, is a standard normal distribution, which is P of X T, the last distribution that we get. What is that distribution in this particular case? It's the point to ponder, but just for the sake of clarity, it's nothing but a kind of considered as a pseudo uniform distribution. So the last distribution is not a Gaussian distribution, as you might have already guessed, but rather a pseudo normal distribution where all the tokens, occurrence of all the tokens, have the same probability. Let's just finally look into that training stage once, and we will move forward. So similarly, what we will take, first we will take an image and a text pair. We will use a VQ-VAE encoder and get the 2D code representation X0, and we will do byte pair encoding to get a discrete encoding of the text. We will uniformly sample any time step like previously. This is very similar to all standard diffusion processes. We will sample from QXT given X0. If you remember, we already have the analytical expression for it. We get the XT, and we will perform the loss. We haven't discussed the loss. We will discuss it later, and then we will update the parameters accordingly. So that's how everything comes into together. Now we only have to look what the loss has to offer and how we will perform the reverse process. And I will move forward and pass it on to Adil.
So I will be explaining the overall architecture now. And before we go into the, as Manu has explained, the forward process, before we go into the reverse process, it will be helpful if we see the architecture first. So we take the input image, we pass it to VQ-VAE encoder, we get the code representations. Then we run the whole forward process and we get the noisy or the masked code representations. Then the authors of this paper introduce a diffusion image decoder, which is conditioned on text here. And the reverse process starts from here. Then the whole reverse process is run to get the noiseless code representations. These predicted code representations are then passed to VQ-VAE decoder to get the output image. So this is the whole process going on here. So now we'll be focusing on the one important aspect, which the author introduced, which is the diffusion image decoder. So the authors propose this decoder, which take tokens at time t, conditioned with text embedding, and output the less noisy code representation at time t-1. So this is the whole idea of this. So how this decoder works? It takes the code representation, noisy code representations, pass it to the first layer of the decoder, which is the adaptive normalization. From this layer, we get keys and values. Then we take the label here, which is text. We pass it to text encoder, which is clip here. Then we get the query from this encoder, and we do the cross intention between the features coming from the code representation and between the embedding of the text. And these process, these two layers, the adaptive layer and these cross-intention layers, are repeated several times in this diffusion image decoder, so that we can get the next less noisy code representation. In this paper, the authors have introduced this decoder at every time t. So when we are time xt, when we are at time t, we use this decoder to get code representation at time t minus 1. And similarly, we use again this decoder to have representation at t minus 2. So now we have seen the overall model and the decoder. Now let's see, the question is how to get the reverse distribution, how the authors are training this particular model. So let's first see the standard reverse process. So the models that we have discussed so far in the class, we see that they predict posterior. And as you can see from the red arrow, when we are at time t, we predict the noise at time t minus 1. This is what usually happens in the standard reverse process. But in this paper, the authors argue that rather than predicting the posterior, if we predict the first noiseless target data, as you can see from the this red arrow, it helps them in getting better synthesis image quality. So what they do, they use a standard cost entropy loss to supervise this prediction, and then use this noiseless token to compute the reverse transition distribution. One more small trick that's introduced in this paper is the fast inference, and it says that some steps can be skipped in the inference procedure. So let's assume a stride t, so a stride delta t. So rather than going from t to t minus 1 and t minus 2 and so on during the inference, the authors argue that they can go directly from t to t minus this stride delta t, and then t minus 2 delta c, delta t, and so on. So the authors discuss that this helps them make the sampling during the inference really efficient with little harm to the quality. So now just try to summarize the reverse process. So we take the text given by this S, pass it to byte part embedding to get the tokens, and we assign sample time t with the number of steps, which is 100 here. Then we sample from the pseudo distribution as discussed by Manu. We start the loop over the time steps, and we use the fast inference strategy. As you can see here, we use this delta stride, and we try to predict the less noisy code representation xt. We subtract the delta stride from the sampling time here, you can see, and we run this loop until we have reached the last time step. And at the end, we pass the predicted or the noiseless code representation to the VQ-VAE decoder to get the output image. So now let's see the training detail. And the interesting part is here is that the text encoder clip, they have taken pre-trained VAT model, where the image encoder is also VQ-VAE pre-trained, and both these text and the image encoder are fixed. So only the diffusion image encoder was being trained in this whole process.
generated images, self-driving cars, augmented reality, virtual reality. It's all around us.
The authors have shown their results on following dataset. First one is the Celtic bird dataset. The second one is the Oxford flower dataset, and then they have MS Coco dataset. The authors have also demonstrated the scalability of their method by using these two large datasets. They have also proposed multiple variants of the proposed model, and it all depends upon the number of the layers and dimension of the layers that they have used. So two different settings are provided. The first one is VQ-VAE small, which has 18 transformer blocks with dimension of 192, and it has 34 million parameters. Then they have VQ-Diffusion B model, which is the base model with around 19 transformer blocks. So they have also provided Diffusion F variant, in which was pre-trained on the large datasets. So they here I will be discussing the comparison and the state-of-the-art methods. So they have shown their results on the following three datasets, and the results are comparable. And with the last F model eventually gets the better results than the others. Here are the few visualization taken from the paper. Now we'll be discussing the ablations.
Yeah, thank you, Adil. Now let's talk about ablations, which are just some experiments that the authors provide to show the impact of their design decisions. One such decision is the number of time steps. Is the number of time steps. I think it's intuitive that increasing the number of time steps improves the results. So when the authors have performed the experiments on the CUP 200 dataset, when the training steps is increasing from 10 to 100, the result seems to improve, but when it further increases to 200, it seems saturated. So given the time complexity and increase in quality trade-off, they have chosen 100 as the default training steps for all their further experiments. And the next ablation experiment is the mask and replace strategy. To see the effect of this strategy, they have introduced something called as mask rate. Mask rate is nothing but the degree to which the input image is masked during training. So basically, when the mask rate is low, we'll see fewer mask tokens in the final time step. And when the mask rate is high, we'll see a higher number of mask tokens in the final time step. So the authors have experimented with this parameter on the Oxford 102 dataset, and we can see that as the mask rate increases, the FID scores have improved until 0.9 and then worsens. The authors have found that using 0.9 as a mask rate gives the best FID score, and they have explained this by stating that when the mask rate is less than 0.9, it may suffer from error accumulation problem. But when the mask rate is greater than 0.9, it may be difficult for the network to see which region needs to pay more attention towards. The next ablation is in truncation, something the authors have introduced called truncation. Truncation is nothing but only keeping the top R tokens at the highest probability in the probability distribution during the inference stage. Here R is the truncation rate. They have introduced this so that it may avoid the network sampling from low probability tokens. Now they have also used CUP 200 dataset to experiment with this with the truncation rate, and they have found that truncation sampling strategy is extremely important for discrete diffusion, and they have found that 0.86 as the optimal truncation rate. We'll later visually look at the effects of truncation in the demo. Now we'll move on to the effect of VQ diffusion was the effect of diffusion image decoder as compared to an autoregressive one like in previous GAN-based methods. For that, let's look at a quick overview. We know that in the diffusion decoder, we generate the entire code vector in one shot at each time step. But in an autoregressive decoder, at each time step, the decoder performs multiple sub-steps to generate the next code vector in an autoregressive method. To find the impact of this diffusion image decoder in the VQ diffusion, the authors have replaced the diffusion image decoder with an autoregressive decoder while keeping the rest of the network structure and all the other settings as the same. Now, when they have experimented with these two models, we can see that here VQ-VAE is the model with the autoregressive decoder, and VQ diffusion is the model that the authors have introduced. And the S is nothing but it's a scaled model. What the authors have found that not only the VQ diffusion is performing better than the VQ-VAE, the fast inference VQ diffusion model, which is the one with the 25 time steps, is actually 15 times faster than the VQ-VAE model, while performing better and giving a better FID score. The same is the case with the base model as well. Now, as a result of these design decisions, the authors have proposed that this model can be used for general image synthesis tasks as well, like an unconditioned image synthesis task and also image synthesis condition on labels. So to look at these examples, they have took the example of generating using condition on labels. So what they have done is they have removed the text encoder network that we're seeing here and the cross attention, and they have replaced it with a class label that is directly being injected to the adaptive LN operators. And they have looked at the results. The results show that even though this model is not specifically designed for the class label condition image generation, it is able to beat some of the previous works that are specifically designed for this task. So now to conclude, let's discuss about what all we talked about so far. First, we looked at the VQ diffusion architecture, which is a novel and effective architecture to generate images from text. And it does this by modeling the VQ-VAE latent space in an autoregressive manner. By doing it in an autoregressive manner, it eliminates the unidirectional bias that we have seen in previous works. And they've also introduced something called mask and replace diffusion strategy, which is then used to avoid the accumulation of errors. Then we looked at some of the VQ diffusion results, and we've seen that it can generate complex scenes better than previous GAN-based text-to-image methods, and also giving strong results on both unconditioned and conditional image generation. Now let's move on to the demo. We were fortunate to have the code of the paper available, and also it was also available in the Hugging Face library. So we performed these following experiments. The first experiment is with 100 time steps and using the truncation rate as 0.86, which the authors recommend. And I've run this on Google Colab, and the inference time is around 160 seconds. So this is what the model has generated when I've given the prompts which have been presented in the paper, the same prompts which have been presented in the paper. And looking at this, we can see that it's pretty good results. So we gave some custom prompts, and these are the generated images. We can see that it is able to accurately generate these random objects like this burger and a car, but it kind of struggles to generate people, at least this particular model that we experimented with. And the next experiment is using the fast inference strategy, which the paper has mentioned, which is basically making the inference time steps as 25, while keeping the truncation rate as 0.86. Consequently, the inference times has come down to 40 seconds. And these are the results that the model has generated with the prompts given in the paper. And these are the results generated by the paper with the custom prompts that we have given. Now to look at the effects of truncation, this is the image that I've shown in the previous slide with the truncation rate 0.86, with the authors have shown as optimal value.
and the prompt is a car on top of a hill. We have generated this image using this truncation rate. Now, when I reduce the truncation rate to 0.75, this is the image that the model generates. Basically, it ignores some of the details and produces a finer image. And then as I further reduce the truncation rate 0.5 and 0.2, we can see that most of the details have vanished and only the base image is being generated. Now, what happens if we don't apply any truncation, basically R as 1, we can see that in we can see some unnecessary details being generated, such as this Shutterstock watermark, which is an unnecessary detail, and these are all the generated images at a different time step, different truncation rate. Sorry. Yeah, and thank you.